All right, good evening, everybody. Welcome back to College Algebra. So here we are with going over some increasing and decreasing and some piecewise functions. Okay, so I thought we would start with this one today because it had a new word in it, and I want to, it's not something we usually use in the pre-calc people. I mean, any class that's pre-calculus, we usually don't use this word, but here's the idea. It says, identify the location and value of any relative maxima or minima of the function. And all they're trying to say is like, well, let me draw you a picture. Okay, because it's a little bit more complicated than they're going to make it seem. Okay, so if we have a graph, okay, and we have some kind of a function on this graph. And we'll give it an absolute endpoint. So we have an absolute min. It's the smallest point on the graph. That's all that means. And then we have an absolute max, okay, which is the largest point on the graph. That's all it is. Well, if you take a look at this point, like in here, okay, it's the largest value of all the values that are surrounding it. Okay, because there's like a turning point here. So this would be called a relative max. And in this point over here, right, where there's it's the smallest point, it's the lowest point in its like little neighborhood of points over here. This would be a relative min. Okay, and absolute maxes and absolute mins are also relative. Okay, because they are relative to all the points around them. They are the relative highest. Okay, they also have the notation of also being the highest point on a graph. Okay, so if we have a graph that looks like the one we have on the value here, right? There's one point that kind of rises above all the other, and you say, well, it's both a relative maximum and an absolute maximum here. Now, this graph does not have an absolute minimum because these both go down, and if you let them go out long enough, right, you're going to get to negative infinity with this. So there is no relative minimum here, but the relative and absolute maximum are at the point 1, 2. Okay, so this function has no relative minimum because it just goes down into the depths of infinities here. So no relative minimum. Oh, they're going to make me check. All right. And it does have a relative maximum. You can have more than one. Okay. But we have one relative maximum, and it occurs at the point 1, 2. And they always want an ordered pair when they're doing this. Just tell people, like, if you live on San Mateo and you order a pizza for delivery, you say, I live on San Mateo. That's great, but you got to give them a cross street. Okay, you can't just say I live in San Mateo. That's a really big street. So you got to give them a cross street. So we need the X and the Y for that one. Okay, so for this function, no relative minimum, no absolute minimum, because we just keep going down and down and down. Okay. And we have both a relative and an absolute maximum sitting right here. Okay. So you have another year or so before this becomes really important, because we really make sure we ask this a lot in calculus. It's actually one of the big things we do in calculus is figure out relative and absolute maximums and minimums. But I don't really remember using that word too much with anybody from any class that's before calculus. Okay, this one, right? We have we have a relative minimum here, but we have no absolute minimums because this goes all the way down. But relative to the points around it, right? If I drew like a little neighborhood around this one, this is the smallest point. And then the 2 points that are the peaks here, they are both the absolute and relative maximums for this graph. Okay, and yes, you can have more than one, that's okay. So this function has a relative minimum, okay, at the point 0, 0. All right, see? And relative maximum actually has 2 relative maximums, right? And by the way, this is an even function too, isn't it, right? If I fold this side off to the other side, right, it has that symmetry. So we're at -1, 4. We're also at +1, 4. So 2 relative. So we have -1, 4, comma, +1. Oops, +1 and 4. All right. So that's, they didn't ask about an absolute, that's fine. Okay, because there would not be a relative, or it would not be an absolute minimum, but a relative one, that's okay. Okay, so let's see here. This one, oh, we're talking about increasing and decreasing. Okay, in the context of a pond. Okay, so we have the depth of the, okay, the depth of, depth of pond. Okay. Sometimes you got to be careful with how they phrase this and what graph they actually give you. Sometimes it's backwards from what you think it ought to be. I don't think textbooks are in the habit of doing that anymore because they're ridiculous gotcha questions. But you never know. And accounting is notorious for trying to lie to you and then give you the wrong answer. Okay, so over what intervals? I should say that's a math teacher, right? What intervals does the depth increase? And then write your interval notation. Okay, here's the depth. So we're going to be talking about the depth increasing, which is going to be in this area right here and in this area right here. Okay, so they're being very straightforward with it. If you got the little skier and he's having a hard time, we're increasing. Little skier, he's having a hard time, the depth is increasing. Okay. So let's see here. It looks like it's about from a 2 to 3. Okay. I once had a student get he got a ruler to check I graphed everything in Excel, and they got out a ruler to do something with it, and it's like, I graphed this as well as I could. We'll call that 4.5. So ever since that, I guess to 5. Ever since that day, I've always written on my graph. I didn't like it. Did they not mean that part? Okay, one last time. So we have 2 to 3. I don't. Depth increase. Oh, union, of course. We'll say 4.5 to 5 now. 4.5 to 5. All right, there we go. That looks a lot better. But yeah, he got out a ruler and he looked at this one, measured it, made sure he actually got it. Wasn't exactly 3. It was like a 3.1 something. Like, would I draw like giant little squares on my Excel graph and try to get the points to like nearly match up? Like, I just suck with Excel. It's not, I'm not trying to trick somebody to try to get you to measure out like how it's not going to work. Okay. Where is it decreasing? Okay, so we have, again, it looks from 0 to about 2. Okay. On the other hand, I did have a physics lab once, 3 to about 4.5, where, and I can't believe I did this. We were having we got this graph out of a magazine article. We had to do something with it, and we were sitting there with a magnifying glass trying to get it, and we turned into the teacher, and they were wrong. Those numbers were wrong. And he looked at us like, "Why don't you just put it in a photocopier and blow it up?" All right. Estimate the times and values of any relative minimum or maximum on the interval. Okay, so at t blah and blah, the function has a relative minimum. So let's find some relative minimums. So we're going to have here, and it looks like here. Okay, so our relative minimum is at 2, 6. T equals 2, 6. And then we have a relative minimum here. And it looks like 7. Yeah, T is 7. I forgot to get the y value. 7. Oh, no, that's not. 4.57. I did get the y value. Oh, 4.5 and 7. Okay, there we go. All right. There's a lot more of those in the fall semester than there was now. Okay, how about relative maximum? So this point here, this is relatively the highest point to every point around it. So what we're going to do is we're going to find, again, it's about a 3 and a 9. All right. Oh, that was it. Okay, that's all they wanted. Okay. This is a very standard kind of a question that they would ask you actually. Well, I would not ask one like this quite in calculus, but there are people that will ask this question in calculus. Okay, so you're prepping for a much bigger day. Okay, produce a rule. All right, so produce a rule for the functions and the transformations. This looks pretty good, right? So when x is less than or equal to -1, right? So if you live in this neighborhood, -1, what's the rule? Well, the rule is constant. Everybody's at -1. Okay. For x greater than -1, right? So everything after -1, what's the rule? And it looks like if I have a 2, we're going down to 4. It looks like -x squared. Okay. All right. So -x squared, that looks about right. That, and you say, well, how do you know that's the way it is? Like, that's the shape it has. Is it looks kind of like a parabola, and it's facing down. So I'm going to guess there's a negative coefficient, right, to flip it. But I'm looking at this point 0, 0. It's not moved around anywhere. It's not up here. It's not over here. So I don't have any shifts to deal with. And then I'm looking at -1, 1, and then -2 down to 4. That's the standard parabola. There's no scaling factors going on. So that's how I'm thinking about that. All right. Let's try another one. Oh, nice, guys. They ran the gambit between A and A. All right. So this one, again, anytime we're before 1, right? What neighborhood are we in? We're in the neighborhood that's before 1. What rule applies to us? This rule does. Okay. So when x is less than 1, then the rule that applies, -x, oops, this one squared. Okay, and again, at -1, it's 1, and 2, it's down here 4. -2, it's down here 4. -4. And then for x greater than 1, okay, so this is the neighborhood we're living in. And what's the rule? oops, 1, and then this is -1. The toughest part about this, again, remember to read it backwards. I want to try, I'm not going to do it if it's the same one. I just want to try one more to see if they're going to give me anything more interesting. Okay, marginally more interesting, but not enough to care. Okay. So let's go with, okay. Wow, I think this is the end of chapter 1.7. Okay. We'll do another one of these too. All right. This, students always have a tough time with this one. Even by hand, they always have a tough time with something like this. So here we go. We have a function negative x squared plus 4. Right? So we have a vertical shift of 4 and then a reflection. 3x, just a line, right? Y equals mx plus b, mx, there is no b. So we need a neighborhood. So when x is less than 2, this is our function here. So we're going to go with this guy. So we're going to place the vertex, 0, 4, place the, is that, and then there was no scaling factor. It's just a reflection, so that's it. So when I placed that second point, I just moved up, one to the side and one down. One quack, one waddle. One quack, one waddle. And it's less than 2. So the spot I'm allowed to use here is less than 2. So everything over here is fine, but anything bigger than 2 is not going to be there. So what we have to do is we have to snip 2, 0. Okay. And then what we're going to do is hit the eraser, and notice only the part that's after the snip carries, or I could get rid of this side. Okay. But that's the part that we're going to snip away. All right. And then we have 3x. So when x is greater than 2, if I plug in 2, right? If I plug in 2 here, then I'll get a y value of 3 times 2, which is 6. So we're going to go up here to 6. And then we need to come up with a slope, right? Our slope is 3. So it's the rise over the run. Yeah, so it's quack, quack, quack. That's 3 points up. And then 1 waddle over. Okay. And again, we are going to snip this graph. So I want the graph 2, 6. All right. So it marks this little mark here. And again, which side do you want to get rid of? Well, I don't want it over here because at this point this fails the vertical line rule. So we have to get rid of this part. Okay. And now what we're going to do is we're going to clean this up. When x is actually 2, which rule am I following? Looks like I'm following this one. Okay. So this one is going to get the closed dot, and this one up here is going to get the open dot. All right. And I think we're good after that. Oh no. There we go. Control Z for the win here. All right, so hooray, we have a good graph here. They were happy with that. And then we're going to write the domain. Okay. Well, it doesn't look like we're skipping anything in the domain, right? The domain is all the legal values of x. Looks like we're okay. So this is a good one. So the domain here, right, is going to be all of the numbers. I hope they ask us the range. They do. Oh, look at this. Okay, these are all the legal values of y. So the highest point on this particular graph is at 4. So we're going to go from negative infinity up to 4. Right? And we need one of these because we actually hit 4. We're going to say negative infinity up to and including 4. But we skip a spot, right? We skip 5. And then from 6, we don't actually start from 6. We just get a little bit away from 6. So this is going to be union. And then we're going to do 6 off to infinity. Okay, and yes, it's okay that a function would skip some values. Okay, so it goes up to 4, we included it. We get to 6, we didn't include it, and then we're ready to go. All right, they're very good. And now they're just going to have us evaluate different numbers. So f of -2 looks like 0. F of 2 also looks like 0 when I consult the graph, also at 0. And then f of 3, see, now we're up here. Okay, f of 3, we got a different rule. We got 3x, right? So we're going to be up here at 9. All right. So it's like, oh, 5 of 7. Oh my goodness. All right. Find all values of x for which f of x equals 9. There's exactly one value, right? If I look at the horizontal line test here at 9, the only point that it intersects here is x equals 3. All right. Okay, so let's see here. Find the values of x for which f of x equals -5. So we're down here. My f of x down here, it looks like it's going to be x equals -3. Oh, this. Okay. Yeah, I'm gonna go ahead and let's graph another one. Okay. Yeah, we're gonna skip. It's fine. Yeah, that's fine. All right, let's do one more so we can graph this thing. No, I wanted another one. What are you doing? Oh, it's 4x. Oh, that's really. Let's see if we can get another one that's a little bit more interesting. I doubt it, but maybe. Yeah, I know. Come on. Let's try another one. These are awful. I used to do a ton of these back in the before times here. All right. So how about we do this? We'll do a f of x equals, and how about we do a x is less than or equal to -3, and the rule. Oops, I wrote it backwards. What am I doing? I wanted to write this. Well, we say x equals 3, and that's when x is less than or equal to -3. We'll say absolute value of x between 3x and +3. And then let's see here. Why don't we do something like 6 minus x for x greater than or equal to 3? All right. Okay. So let's check out each of the neighborhoods. Okay. Let's go ahead and do this. Let's use that grade. Okay. So when x is less than -3, 1, 2, 3, what's my rule, right? I'm in the neighborhood that's over here. My rule is 1, 2, 3. And it's got an equal sign, so we're going to use the closed dot here and a nice constant function. Okay. Now, between -3 and +3, then we have this absolute value of x. And the absolute value of x is going to look something like this. All right. And then when we get done with 3, we actually need an open dot here. the open dot because that's not really there, right? It's not quite there. And we look at 6 minus x, right? We're going to do 1, 2, 3. So there's 6. When x is 0, we're at 6. And when x is at 6, then y is 0. And we only care about it from 3 onwards. So at x equals 3, we're at 3. Okay? And that would be the graph of this function. Okay. So that's let's do one more. Okay, so let's go with f of x equals, and let's take a look at this. Go with 1 from x equals 0 to x equals 1. And let's do a, let's look at a 1 minus x squared from 1 on to 2. And then how about we do a cube root of x, and I want to make this something I can take the cube root of. How about we do that? All right. That looks terrible. Yeah, I guess so. All right, we have to get a graph from 1 to, or from 0 to 16. All right, because most of the action is going to take place over here, right? So let's make our coordinate system. Okay, so when x is between 0 and 1, right? Let's go with 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 3, 4, 5, 1. There's 16. So 5, 10, 15, 16. All right. Now between 0 and 1, what happens? We have a dot at 0. We have a dot at 0 and an open hole here. And we just have, oh no, we don't have that. We have constant function. Boy. Teaches me to do that. All right. So we have a constant function between 0 and 1. All right. Then after from 1 to 2, we have 1 minus x squared. Okay. So when x is 1, we have a 0. And then at 2, right, we're going to be at 2 squared. 1 minus 2 squared is going to be negative 3. So let's go 1, 2, 3 down here. All right. And it looks like we have dots on both of these because they're equals on both of these. Okay, and then from 2 on to 16, we have the cube root of half x. So if I plug in 2 into here, right, we get half of 2, which is 1, and the cube root of 1 is 1. And then if I plug in 16, right, half of 16 is 8, and the cube root of 8 is 2. There's a nice blue. So we're going to go from 1 all the way up to 2. And we're just going to get something kind of a graph like that. Okay, and those, okay, that was terrible. Okay, let me double check to make sure we have, oops, this should be an open dot. Okay, these are closed, open. So does it Does it survive? Does it pass the vertical line test? Like, yeah, it does. I mean, things get a little squished in here, but if I try to do a line here, function doesn't really work there. It's an open hole. It only hits it once. Okay, same thing here. It's an open hole. It only hits it once. And then everything else is fine. All right, these are, okay, I know these examples are harder than the book will give you, but if you can do one of these, you got everything the book is throwing at you. All right, so we're good. All right. So there we go. Those are piecewise functions. Again, I know they're a little weird, but you know, it is just the same thing as the rules are different depending on where you live. And adults, we can deal with that. Kids have a harder time with it. Well, I shouldn't say kids, but you know, recent adults have a harder time with this. They're still under some delusion that life is going to be fair. Everybody who's older knows. Our tax rates are based off a piecewise function. Okay, if you make certain amounts, right, you know, depending on how much you make, you get a different percentage that's applied to that amount that's over. Okay, so it does exist. It does come up, and you know, you'll see that. I had one student argued with me on that one. Like, I'm not, you know, I'm not telling you one way or the other how to think about taxes. I'm just saying, like, you know, this is how our taxes work. I'm not at fault for I refuse responsibility for any of that. I don't have any power. Shoot. All right, let's get rid of this. We'll go on to the next one. Okay, so that's 1.7, and then let's jump into 1.8 here. Click out of that and open that in a new window. We'll hit our assignments. Sorry about that. I don't want to scroll down on that at all because there's I get notices. Okay. Oh, you guys are going to like this one. By that, I mean you're not going to like it at all. So let's do a preview of this. Okay, so this starts off pretty tame. All right, this does start off pretty tame. All they're saying is, if we had two functions, right? If I had f of x and g of x, and I have f of x is equal to x and g of x is equal to x squared, well, then f of x plus g of x, we can write it as f plus g of x, and that is going to be x plus x squared, and that's going to be x plus x squared. Okay, so all this is doing is saying that you can add two things together, or more than two things together. We could also subtract them, right? We could say g of x minus f of x. That's going to be x squared minus x, and that is x squared minus x. Okay, so that when you see this f of x plus g of x, f of x times g of x, okay, that's a dot, not a next thing we're going to see, then we can just multiply them together. Right? Or if we divide them, you know, we can say f of x divided by g of x. So it's going to be x over x squared, which is 1 over x, provided x is not 0. Okay. All the way around, the same idea, right? So g of x over f of x. We have x squared over x. Now here's where it says, provided x is not 0, because this is what you start with. That's equal to x. So the answer is x, but we have a caveat, x is not 0. all it's going to look like is that we're going to have y equals x. But if you look real close, we're going to have a little circle at the middle because x can't be 0. Okay, because we started with this, we always have to go back to this. Okay, you always have to go back to your original functions when you're dealing with this stuff. All right, so the two examples I have for that are I can't remember his name. It's the first ghost that Scrooge meets, right? His old business partner who's got all the chests wrapped around him. You have to drag all this baggage around with you all the time. So when you finish your answer, it's like, great, I got a nice answer. I'm like, yeah, but you got this baggage you have to go back and deal with. I think it was Marley, something like that. But you have to drag this. The other thing is, I don't know if your family is anything like mine, but you know, there are certain topics that'll come up during Thanksgiving, and people will have a giant fight over it. And even though that relative has passed away, nobody will ever bring up that subject ever again because of that one fight that we had. So you have to drag this stuff around for the rest of the problem. Okay. So just like your family has to drag around that fight forever. Okay. This one is pretty straightforward. Like I said, they're just going to ask you f minus g. Okay, so what do we start with? F is 2x, g is absolute value of x plus 5. So we got 2x, we got minus x plus 5. We don't have to simplify any of that. It's fine. Okay. Oh, but they want us to put in 4. Okay, let's put in 4. This is f of minus g. At f minus g of 4, we have 2 times 4 minus absolute value of 4 plus 5, absolute value. So we just have 8 minus absolute value of 9. What is the absolute value of 9? It's always the positive. Okay. 8 minus 9 equals negative 1. So wait a minute, you have a negative number in there. Let's see, did I keep this? I did. What was the graph? Desmos, by the way, this is one of the most awesome programs that there is. If you're not using Desmos to help you, you know, it's one of those things. It's a great tool for doing a lot of math, and visualizing is fantastic. Okay, minus. And if you do this, I put that button, or I think you can do this, AVS. And I think we could say x plus 5. Well, it didn't complain. Oh, there it is. Okay. I knew it was like some kind of a bend in here eventually. But you know, let's do it this way. Oops. Oops, I want 2x minus this thing, x plus 5. And notice there's a lot of negative, right? There's a lot of negative values on this graph. So even though it has an absolute value in it, it's okay for it to be negative. And what did they want to know? They wanted to know where negative 4. So if we go down to negative 4, we end up with, right, negative 4, negative 9. By the way, good for checking your homework. Do not rely on this to do your homework. If you're stuck, this is a great tool. If you want to check, this is a great tool. You just want to say, I'll let Desmos take care of it. Like, that is a terrible tool, because when it comes to the exam, you're not going to have this website, and then you're going to get stuck. So this is a wonderful tool, but don't abuse it. Oops, what did I want to do? I wanted to go here. So, oh, positive 4. What am I doing? Negative 1. Okay, I think that's what we had, right? Yep, sure was. All right. Are we going to ask me more? No. Okay. skip this one. That's a little bit easy. I wonder if they have the hard one. Yeah. If they don't, then, by the way, my pre-calc class had this problem too. They had slightly different problems. You guys are in for a treat when it comes to the stuff here. Did they not do function composition? Oh, they do. Okay, thank goodness. All right, function composition. This, of all the things that we can do with the function notation like this is probably the hardest one. Okay, so we have G and H here. Okay, so G is the value of 2, or square root of 2x. H is equal to, h of x is equal to 6x plus 7. And we want h of g of x. I'm also going to ask you what g of h of x is. Okay. Now, what's going on here? Okay, the notation I really wish they would have said is this thing. Okay. This is normally the notation that they introduce you to, and this is how to evaluate it. Okay. So let's start with a number and see where we're going to go with that. So we'll do h of g of x, and then we'll start with a number like h of g of x, and we'll start with a number like what happens when x is equal to 2. Okay, so what we're going to do here is we're going to say, well, g of 2 is what? Well, it's the square root of 2 times 2, which is the square root of 4, which is equal to 2. All right. Now we're going to take this 2, this one right here, and we're going to plug it into h. So we're going to say, well, what's h of 2? And that's going to be 6 times 2, right, plus 7. That is equal to 12 plus 7, which is 19. Okay. Let's try another one. Okay, let's see. How about 8? Okay, how about we let x is equal to 8? So we want g of 2, or g of 8 rather, is equal to the square root of 2 times 8. It's the square root of 16, which is 4. Now we're going to take this 4 and we're going to say, well, h of 4 is equal to 6 times 4 plus 7. Okay, which is 24 plus 7, which is 31. Okay, let's do another one. Let's do one where we had 25. 36 works. So 2 times what? 2 times 18. So let's let x is equal to 18. So h of 18 says the square root of 2 times 18. That's the square root of 36, I believe, which is equal to 6. Now, I'm going to take this 6, and we're going to say g of 6 is equal to 6 times 6 plus 7. Right. So do you see what we're doing? We're evaluating the inside function at the point that we have, and then whatever the output of g of x is goes into the input for h of x. Okay, so we have, we have g. So here's the picture they usually draw you. And so g of, oh sorry, h of g. So they have a domain of g, which gets mapped into the range of g, but also we're going to call it the domain of h, and then that's going to go out to the range of h. Okay, so we're starting with some x's. In this case, right, our x's can't be negative numbers. Right, 0 would be okay. The square root of 0 is 0. I put a -1 in there, not so good. So this domain here, this has got to be x greater than or equal to 0. Right? And that's going to go into its range. The range, again, this is all positive numbers. Okay. So the domain of h are these positive numbers, and then it's going to spit out the range of h as our answer. Okay. So we're going to feed g a positive number. It's going to give us back the square root of twice that number. And then at the same time, we're going to take this output and we're going to feed it to h rather, and h is going to pop out the result that we have for h. Okay. So it's kind of a two-step process here. We figure out g, get an answer, and then feed this answer in for h, and go for the next one. Okay. I had a risk management teacher who would, his tests were always 6 questions, sometimes less, actually. The answer to problem number 1 was your input to problem number 2. If you didn't get the first one right, then he stopped grading the rest of the exam because they were all wrong. Because you didn't get the right answers to come out, so you were done. So for him, to be fair, getting a 3 out of 6 in that class, that was an A. Okay, getting a 2 out of 6, that was a B. And getting 1 point, which means you got most of the way through problem number 1, or you got all the way through problem number 1, and biffed on problem number 2, then that was a C. Okay, so pretty much all you had to do was grade mostly 1 problem. If you and nobody got more than a 3. Nobody ever got like more than half of them right. So if you got to problem 3 with that, it was a miracle. But that's what he would do. So you can think about the function composition like that too, right? We get inputs, we do a problem, we get an output. Hopefully it's right. Problem number 2, that's the input, spits out for the output for problem number 2, and you can take this thing and shove it into problem number 3, and hopefully you're still going. So that was what he did. Yeah. So the idea here is, are they the same on both sides? Let's see. What if I put in x equals 2 here, right? We have h of g. Let's look at g of h. Let's look at, what if we have h of 2? Well, that's 6 times 2 plus 7. So that's 12 plus 7 is equal to, right, is equal to 19. And then g, right, g of 19 is equal to the square root of 2 times 19. Is that 20? That's the square root of 38. I'm going to suggest that the square root of 38 is way different than 19. Okay. So these are, this is not the same. So you can't say g of h of x is equal to the same as h of g of x. All right, it doesn't work that way. So this is one of the few things that you know so far that does not commute, right? You can't swap it by say f of a with some kind of an operator. Usually that's an operator that you don't know. Times, divide, minus, plus, whatever. Okay. This is not the same as f of b star f of a. Okay. Because they just don't do that. They're not related. Okay. I think I should probably stop there because it's been a long night so far for everybody. We will pick up with 1.8 because we're gonna need some time on this one. That's okay. There's some stuff here that's a little bit terrible. Okay. So I'm gonna go ahead and say goodnight to everybody that's listening.